So hello and welcome to this course Machinery Fault Diagnosis and Signal Processing. In today's lecture we are going to see some of the advanced signal processing techniques which are used in condition based monitoring. In the previous lecture also we have seen there are various signal processing techniques by which vibration signal or an acoustic signal can be processed, such as time domain analysis, frequency domain analysis, time frequency analysis, order analysis, envelope analysis, etc. Out of which in the previous videos we have seen time domain analysis and frequency domain analysis and particularly fast Fourier transform we have seen in very detail. Now we know that the frequency domain analysis is required because time domain analysis has a limitation that the time domain statistical parameters are very inconsistent, and purely relying on time domain analysis is sometimes may lead to a faulty conclusion. So time domain analysis has to be associated with frequency domain analysis to have some concrete conclusion. And another disadvantage of time domain analysis is that it doesn't give it only indicates the presence of fault, it doesn't give the exact location of the fault, and that is why frequency domain analysis is important to detect the exact location of the fault, and that is why frequency domain analysis is very important. Now the time domain analysis and frequency domain analysis is explained from this picture. So if you plot a signal in a three-dimensional axis where the horizontal axis, x-axis indicates time, y-axis indicates amplitude, and z-axis indicates frequency, then if you see the signal in xy direction, then you can see the time domain analysis, and if you see the signal from yz plane, then you can see the frequency domain analysis. Okay, so the signal is same, only the viewing direction is different. Now why what are the limitations of frequency domain analysis, or particularly what are the limitations of fast Fourier transform, that we will see. We have seen that because the impact generated by bearing faults or the impact generated by any machine fault, it distributes its energy over wide frequency range. Thus the bearing characteristic frequency has relatively low energy, and it is often overlapped by surrounding sound. So fast Fourier transform basically used for low frequency analysis, and the problem with analyzing a signal in low frequency zone is that in low frequency zone, along with the bearing characteristic frequencies, there are other contaminated frequencies are also involved, and the signal in low frequency zone get contaminated because of the surrounding frequency, and analyzing such a contaminated signal may lead to some faulty conclusion, maybe some inconclusive conclusion. So that is why there is always a risk component involved while analyzing a signal in low frequency zone, and these characteristic fault frequencies are traveled to high frequency zone with the structural resonance frequencies, and if you try to separate the fault frequencies with the structural resonance frequencies in high frequency zone, then the signal analysis or the conclusion about the location of the fault may be very precise, and that is why it is always recommended to analyze a signal in high frequency zone rather than low frequency zone. These fault frequencies are carried by structural resonance frequency into high frequency zone, hence the frequency study in low frequency zone may give decisive results. Okay, and that is why there is a need of some advanced signal processing techniques so that the decision making should be precise. Now, what are the other frequency domain analysis, or what are the high frequency analysis techniques? So, fast Fourier transform is basically used for low frequency analysis, but in high frequency analysis where the fault frequencies are carried to high frequency zone with the structural resonance frequencies. So, for analyzing such modulated signal, because the signal gets modulated because the fault frequency are carried by the structural resonance frequencies and the amplitudes are modulated. So analyzing such modulated signal, we require envelope analysis. So generally high frequency analysis is carried out by envelope analysis. So envelope analysis is one of the advanced signal processing that we require for analyzing a signal in high frequency zone. So how this high frequency analysis is carried out? In the envelope analysis, a defective signal produced in an amplitude modulated signal with the bearing structural resonance frequencies as the carrier frequency, and the modulation of amplitude is by bearing characteristic frequencies. So the fault frequencies are modulated because of the structural resonance frequencies, and these fault frequencies are carried to high frequency zone by these structural resonance frequencies, and because of that the amplitude get modulated. So to demodulate these modulated signal, this envelope analysis is carried out, in which envelope is detection. So one of the step is envelope detection, in which the amplitude demodulation is used to find out the repetitive impulse type signals. Okay. So the complete methodology of envelope analysis is explained in this chart. So first is a vibration signal, a faulty vibration signal. Then we use a band pass filter around excited natural frequencies. So we take a band pass filter particularly in high frequency zone, then take the Hilbert transform of the band pass signal and take the magnitude of analytical signal to obtain the envelope signal. Now these signals are enveloped. Here you can see that in the blue color, this is the modulated signal, and these modulated signals are enveloped by using these red dots, and then the frequency of these red dotted wave is find out by using fast Fourier transform, and from these frequencies you can actually find out the location of the fault. Okay, so this is how the envelope analysis is carried out. So this amplitude modulated signal is enveloped from the outer boundary, and then the frequency of these envelopes or frequencies of these red dot signals are taken to find out the location of the fault. And for taking the envelopes, Hilbert transform is used. So there are several algorithms available to perform high frequency envelope detection effectively, and one of the most used method is through the Hilbert transform. It is a mathematical variation to the fast Fourier transform which demodulate a vibration signal and extracts high frequency low amplitude data of interest. So this is how the Hilbert transform works. We will see this working of Hilbert transform in details in the coming lectures. The another technique of envelope detection is order analysis. So order analysis is more complex method of envelope detection. Actually, this order analysis is inbuilt algorithm available in National Instruments sound and vibration suite. So in the National Instruments LabVIEW software, in the LabVIEW software there is sound and vibration suite. So this order analysis virtual instrument is ready-made available in the LabVIEW software, and from that you can directly use this algorithm. It is an already filtered signal is fed to the virtual instrument, and envelope spectrum is obtained as an output. So the band pass filter signal is given to this VI, and the output you can find out as an envelope spectrum. This VI extracts the modulating signal from an amplitude modulated signal. This technique is particularly useful to identify the mechanical faults that have amplitude modulating effect on the vibration signal of a machine. So the Hilbert transform or order analysis both are used for the envelope detection and to demodulate the signal from the modulated signal in high frequency zone. So these are very advanced signal processing techniques, and by using these advanced signal processing techniques we can actually find the location of the fault in very precise manner. We will see these advanced signal processing techniques in very detail in the coming lecture. So thank you very much.